Multivariable calculus, we're still in section 13.4, day 2, and take a look at the very top of the notes here. It says, when we study the motion of a particle, we often want to resolve the acceleration vector into two components, one in the direction of the tangent and the other in the direction of the normal. This happens quite a bit in physics. So we're going to derive that very breaking into those two components. Normally our components are in the x and y directions, in the I vector and the j vectors directions. But today we're going a little bit differently, and there can be great practical insights from it. So look at the unit tangent vector t. By definition, it was r prime all over the length of r prime. So it's the velocity vector divided by the length of the velocity vector. So the velocity vector we can write as v, but rather than have to write the absolute value of the velocity vector repeatedly, look at what we have in yellow here. Just a v without an arrow, lowercase. That means it's the length of the velocity vector. And that's going to help us out considerably. So t is equal to v prime all over v without an arrow, or v prime, v with that arrow, vector v, all over the length of v. If we were to solve for vector v, we'd multiply by this yellow highlighted length of v. So it'd be v times vector t. Now, please do understand that the length of the velocity vector, whether we look at that in terms of the absolute value or without, when we don't have the absolute value, of course, we don't use the arrow. I guess what I'm trying to show you is v, or this length of the velocity vector. It does not have to be a constant. It could be a function of t. And, that's very, very important where we're going next. The acceleration vector is going to be the derivative of v. So come back right here. How do we take the derivative of just v times vector t? Well, we're going to need the product rule. We'll have this derivative of this length of the velocity vector, v without the arrow, that's v prime times t, plus now take the derivative of the tangent vector t prime multiplied to v. So we get this right here. So that's going to really allow us to look at our acceleration vector. Now, the acceleration vector, you can be quite content and happy. You can say, hey, now I have a component. I have part of this vector represented as t, something multiplied to the tangent vector. I'd really like to get to the normal vector. To do that, let's review a little bit. Remember kappa. Kappa right here was the length of t prime all over r prime. And r prime in absolute value, that's really r prime is v. It's the length of vector v. So we could just write it as v without that vector arrow. So what are we really getting at? We're seeing that solving for this t prime's length, we can say that would be k times v if we just multiplied by v on both sides. So here we have this. But here's the connection. The normal vector was t prime all over the length of t prime. Now, we just solved earlier, and we're going to use a substitution to help us. But first, let's get t prime alone. If I multiply the right side and the left side by the length of t prime, we're going to get what we have in blue here. T prime is the length of t prime times n. But look where we're going with this. We can say, wait just a second. This thing right here is kv. So we'll have kv times n. So that's what T prime is. Now let's remember what we came up with earlier. Earlier in, let's maybe change this back over here to yellow. We saw that the acceleration vector, this acceleration vector was v prime t plus v t prime. But what we're really seeing right here as we're putting it all together, we're going to be able to substitute this in. What is t prime? We're seeing that t prime is kvn from what we just saw here. So we can substitute that in, and we have our v prime t, but here we have v times kvn. And of course, that's going to become kappa v squared times vector n. That's what we've got right here. So this is our acceleration vector broken into a combination of two different vectors. We're breaking it into components of a tangent vector and a normal vector. Notice the subscripts here. When we write a sub t, that's the tangent component of our acceleration vector. What's in front of our tangent vector? Well, it's going to be v prime. What's in front of our normal vector? Well, that's your kappa v squared. So that can really help you out. You'll be able to use that formula. But notice that the binormal vector, we always saw in our previous sections that the tangent vector, the normal vector, and the binormal vector were all working together for so many problems. Notice that the binormal vector b is absent. So no matter how an object moves through space, its acceleration always lies in the osculating plane determined by the tangent vector and the normal vector. Furthermore, the tangential component of acceleration is v prime, which is the rate of change of the speed. That's what v prime really is. And the normal component is kappa v squared. So the curvature multiplied to the square of the speed. So how can we see this in a physical interpretation? Remember that the unit tangent vector gives the direction of motion, and n points in the direction that a curve is turning. So let's say that you're driving at a relatively high speed and you're beginning to accelerate. Think of a passenger in a car making a sharp turn with large curvature. The component of acceleration perpendicular to the motion in the normal is large. And that's why you can see people and objects being thrown inside the car, feeling that force as they are making a hard, sharp turn. So here's the thing, as we continue on, we would ideally like to not just have these two components that we have right here. There's nothing wrong with them, but we'd like to instead maybe find a formula for the tangential and normal components based exclusively only working with r, r prime, and r double prime. So let's see if we could perhaps just break this into play. So remember what we just saw a moment ago. The velocity vector is really the length of the velocity vector times the unit tangent vector. That little v there without the arrow is really the length of the velocity vector. So let's just consider the dot product of v and a. Well, we just saw what v is. We could say, well, instead of writing velocity vector v, let's write v without an arrow, little v, and here's our t with our arrow, and we're going to dot product that with Well, what did we just find our acceleration vector to be? Well, we broke it into a tangent component and a normal component. And I'm just going to rewrite that right there. So at this point, if we did our dot product, well, you can see what's going to happen. We'd have our v prime, and then we'd have our unit tangent vector dot producted to itself. Then over here, we'd have a v and a kappa. Well, that's a kappa v cubed. But then we'd, of course, have our tangent vector dotted with our normal vector. Well, let's have a little bit of review. Remember from our dot products, when we had A dot B, that was always the length of A, length of B, times the cosine of an angle between them. Well, what if we looked at the dot product between a unit tangent vector and itself? Well, we'd have the length of the unit tangent vector times the length of itself right here. But what's the angle between them? Well, 0 degrees or 0 radians. So we'd have a 1 times a 1 times what's the cosine of 0? Well, it's also a 1. Wow, what are we seeing? T dot T is actually going to be a 1. Breaking this down with the tangent dot producted to the normal, remember that these are orthogonal vectors. They make 90 degrees with each other. And that means the cosine of 90 is 0. So remember, the dot product of orthogonal vectors is always 0. So what are we getting at? Well, coming back down here, we have v prime, but this dot product of t to itself is just a 1. And of course, this all is going to go down to 0. So what did we just see? We just saw very quickly that v dot a is equal to v without an arrow times v prime. So that hopefully is going to help us out. And right now I'm going to take this and say, what if we solve for v prime? Well, if we solve for v prime, that would be saying that v prime is velocity vector dot producted to the acceleration vector divided by v. Okay? So that's really where we're going. Tell you why we wanted that. When we went back to our page 1, we saw that the tangential component was v prime. So we just solved for what v prime is. It's going to be v dot a, velocity vector dot producted to vector a, all over the length of v. So therefore what we have is, well, the velocity vector was r prime. The acceleration vector is r double prime. And v without the arrow is the length of the velocity vector, so it's the length of r prime. So wonderfully, what we're seeing, guys, is we have now found a formula for the tangential component of acceleration. We've got it right here. So that's wonderful news. Now, we're getting close. We're going to be able to also remember from 13.3, we saw that kappa, the curvature, had a wonderful shortcut formula. It was the length of r prime cross-producted to r double prime divided by r prime of t's length cubed. Well, that's really going to be able to help us out right now as we work on the normal component. And we're going to pick this up in our next video.